Hello, this is Jonathan Templin, and this is a lecture that is an introduction to generalized univariate models, where we're going to start with models for binary outcomes. And this is a lecture in EPSY 905, Fundamentals of Multivariate Modeling. So today what we're going to cover is a short review of maximum likelihood. There's a typo right there. And we're going to then expand upon your linear models knowledge to models for outcomes that are not conditionally normally distributed. So what does that mean? Well, we've seen up to this point linear regression models where the outcome has this assumption that it was supposed to be conditionally normal. So normal, conditional, once you predict it, that the term should be normal. The key thing with the normal distribution is it's not only a symmetric distribution, but it is it's a distribution for continuous variables. So clearly, in the case of a binary variable, so a variable that's a 0 or a 1 with two categories, it is not a continuous distribution, and the normal distribution will not work well for it. So instead, we're going to call upon a new class of models called generalized linear models. The "ized" means more than just normal. And then we're going to let those do the analysis for us. And what we're going to see is this is part of the trend in statistics where if our data don't meet the assumptions of a model, we no longer try to manipulate the data to squeeze it into the analysis that we have before. Instead, we change the assumptions of the analysis to better match the data. And so we're going to then use this to further our knowledge of maximum likelihood, picking up from our previous lectures, and talk about how distributions and likelihood functions make virtually any type of model possible in theory. And that's the key. And then in the future, as we go forward, you're not going to have to worry about again, normalizing your data or doing some other type of transformation for it. Instead, what you're most likely going to be doing is changing the type of model, changing the family of distributions to better match and to better mirror the outcome that you have. So we're going to then get into an example of generalized models for binary data. Again, 0, 1 categories, a discrete variable, sometimes called dichotomous. And we're going to use logistic regression for that. You may have heard of this before. But today we're really going to go deeply into what it is and how it works. So let's go and review maximum likelihood to begin with. We like maximum likelihood estimators because they provide when we meet the assumptions of the estimator, they provide us with some very nice properties that lends a lot of trust to the numbers that come out of the computer. Those properties are described as asymptotic consistency, meaning as n goes to infinity, which is another way of saying the bigger and bigger your sample size gets, the estimator converges in probability to its true values. What does that mean? So the estimate that come out of the computer have with probability 1 the true values of what they should be, meaning you get the right answer, which is a good thing to have. But again, that's assuming the assumptions are met, or the regularity conditions, an illy formed description of what assumptions happen to be. Another part that we get from this is asymptotic normality, which means as your sample size increases, the distribution of the estimates are normal. So the distributions are normal, which is great because now we are able to do things like our Wald test, where we took our estimate, like beta hat, and divided by the standard error of beta hat. That thing is called a Wald test. Usually it has a z distribution, although we can trick this into having a t distribution if we do certain things. That's where you normally see it come out of the computer, out of R, for instance, when we do linear models. But this z distribution relies upon a normal distribution, and that's where it comes from this asymptotic normality over here. And finally, the nice thing about this is the other nice property, or one other nice property, is that the estimates are considered to be efficient in that no other estimator will have a smaller standard error across the range of values that you have. So because of these properties, maximum likelihood estimators tend to be the gold standard for what we do. Although I will say that in recent years and in future years, Bayesian statistics has moved forward, and sure enough, Bayesian methods share these principles with maximum likelihood as well. So things that are involved in a maximum likelihood, in maximum likelihood estimation, we have to figure out the density function, for each variable. So this is the outcome. And we talked about before how that outcome has to map onto the sort of the range of values of the outcome have to map onto the sample space of the distribution, right? We have to make sure that our distribution that we're choosing is discrete, for instance, if we have a discrete outcome. Or if we have a continuous outcome or something that's plausibly continuous, we can pick a continuous distribution. But we can pick any distribution for the outcome that we'd like to do. Once we have our distribution, we form our what's called the joint likelihood function, which is the likelihood of all the data points put together. This is the product of that distribution function, so the height of that distribution evaluated for each piece of data, multiplied across all the people in the sample. So that's what we do. And that joint likelihood function there is what we try to maximize. That's where the maximum comes from, a maximum likelihood. But often what we end up doing is using the log likelihood instead of the actual likelihood itself, because log likelihoods tend to work better, particularly when we have the product of very, very small numbers, because the log of a very small number becomes a negative number. Number that's decimals away from 0. So that's typically what we see is we try to maximize the log likelihood function. And how the maximization process works is this process called optimization, finding the maximum, finding the optimal value. We start by taking an initial guess of our parameters, calculate the log likelihood, and then we go and find new values. Usually it's an efficient guess using some type of calculus-based method, something like Newton-Raphson, let's call it that, where we guess a brand new set of parameters that are supposed to be toward the peak of this distribution, or this function, and then we check again. Check the log likelihood. Check the difference in log likelihood. And if the change in the log likelihoods is small, then we can stop, effectively saying we're at the maximum. But if not, we keep going. We keep doing that process of guessing parameters, getting the log likelihood, checking to see if the change is small. But once we find the maximum, now the sample, the nice thing is that the good properties are at the peak. The distribution of the parameters, for instance, as the sample size gets large, the parameters follow the parameters of the model. These are the betas, effectively, follow a normal distribution, right? So this thing follows a normal distribution. And the true value of beta is in the mean, and the variance covariance matrix is given by something called the information matrix, or the inverse information matrix. But we don't have to go into that. But that's where we get our standard errors. It's based on the model as well, which is nice. We also get our covariance amongst the parameters from this, and that's why we had to, for instance, use the GLHT function in previous lectures and in homework, because this would allow us for linear combinations of parameters to find what their standard error happened to be. Remember, if we took the sum of two betas, the standard error, or the variance of that thing, would be the variance of the first plus the variance of the second, plus 2 times the covariance of the two. And so we get all of that from this thing called the information matrix. So that's nice to have. Furthermore, we get to enable a bunch of other fun things. We can do likelihood ratio tests. This tests nested models. We can see if a model, one model is preferred to another. So if a model with more parameters is preferred to a model with fewer, we can use this. It's a chi-square test. It's convenient. It works for all maximum likelihood so long as the models are nested. And by nested model, I mean a model, what we call the alternative model, the bigger model, subsumes or has all of the parameters of the null model, sort of the smaller model, in it. So there's some type of combination of parameters from alternative, maybe setting them equal to 0 otherwise, that can give us the null model. Finally, we can also get walled tests. This is our parameter estimates themselves. These are the p-values that come directly from the output. And finally, if we don't have nested models, we can do something called use information criteria to determine which model is preferred. But I will say the information criteria, these are only for used in non-nested models, because with nested models, we'd want to use this likelihood ratio test. It's something called the uniformly most powerful test. It is the best that we can do. Okay, so now that we've got a little bit of maximum likelihood out of the way, let's talk about generalized models a little bit. This is going to get kind of crazy, but once we get to the data part, I think it'll be a little bit more understandable. But let's talk about the big picture worldview of statistics. a lot of our statistical models can be broadly organized as general, right, which really became general linear model or linear models, is where we have a normal outcome, versus generalized. Right? Generalized includes the normal outcome, but it also includes a bunch of other, or almost any other distribution, a not normal outcome, a non-normal outcome. And the other way we can characterize this is the dimensions of sampling, right? Perhaps we have one variance per outcome versus multiple dimensions of sampling, right? So maybe we have an example of multiple dimensions of sampling might be perhaps you have an outcome like the probability or the outcome is a binary indicator of whether or not a person graduated from high school, and you want to see if an intervention helps students graduate. So you collect data from all the high schools or a sample of high schools around the state, and you end up seeing that the probability of, you have sort of an error for the outcome itself, but then you also have an error that might be the variance associated with students from the same high schools, this clustering effect of the data themselves. We're going to get to those types of models after spring, later in the semester as we go forward. So all models that we have fixed effects, which means they apply to everybody. And then general linear models assume a conditionally normal distribution for data with no random effects. That's that multiple dimensions of sampling. The general linear mixed model is conditionally normal for data with a random effect. But then we get to what we're talking about today. Generalized linear models is for any conditional distribution of data, and we have fixed effects that makes predictions through these things called link functions, which we'll see in just a moment. And we also have generalized linear mixed models, which are sort of a really crazy set of models where you can have any conditional distribution for data, and you can have fixed effects like you normally have, but also random effects. Maybe there's a random intercept for high school here, like we were talking about before, and those also use link functions. So the linear part of these models comes from the part where we see the betas themselves. So if we take the fixed effects, we may have a beta 0 plus a beta 1 times x, and so forth. That part is linear, and that part still maintains throughout all of these models. However, it sometimes gets put into something called a link function, which means we sort of take a function of that linear part of the model, and this function maps it, right? So if we think about this, these betas can be any number on the number line, and x can be anything. So really the output of this linear combination is a number that goes from negative infinity, potentially goes from negative infinity to infinity. But if you have an outcome that's not on that same space, we need some way to map that onto the space of the outcome, and that's what this link function does. It maps it onto a smaller space so that we can appropriately model the data that we have rather than trying to make predictions of things that don't happen. For instance, the probability that someone graduates high school is 1.2. The link function will prevent that from happening. So here's sort of the big picture. Right, so we have an outcome. We usually think of this as the y part of the model, right? And it can be any distribution. You can have any type of thing that you want. And we always build a model with y equal to, and over here we've got, perhaps let's put our typical beta 0 plus beta 1 x plus, and I'll just put dots. This part on the right-hand side really comes from the theory that we end up having, some type of theory that predicts, that says, hey, x has a role in predicting or causing what y happens to be. And so that still holds, right? That still is the process that we see. However, not all outcomes follow this linear type of model. So what we may have to do, really if you think about what we did in the linear regression sense, the model for the means, as we would call it, would predict the mean for y, or sometimes we denote that as the expectation for y. In a generalized linear model, the same type of thing happens. It's just instead of the model for the means directly predicting it, we have some type of what we call link function. Usually it's a g, and I'll put a negative 1 there, and you'll see why in just a moment. But basically this function now allows us to take that prediction in a linear space and map it onto the space where the mean exists in the data themselves. So the goal of generalized model is to map that theory, substantive theory I call it. It has some substance to it. That doesn't mean the quant stuff doesn't, but it does. This is some type of theory that has been formulated that says this predictor is influential in predicting what y happens to be, and perhaps even causes y. That theory, the generalized model takes that theory and maps it onto the sample space of your observed outcomes, right? So basically, it says you've got this theory of how predictors should work. We're going to let them work in their linear sense, and then we're going to take the result, and then we're going to map it onto the space where the outcome exists. The mean of the distribution exists, right? So for instance, in a binary variable, something that could be 0 or 1, the mean is a number that ranges from 0 to 1. It can't be bigger than 1 because there are no numbers bigger than 1. It can't be less than 0 for the same reason. There are no numbers less than 0. So therefore, we have to take this entire number line and somehow squeeze it into the space between 0 and 1. But the same theory still applies. We can see whether or not variables are influential based on their beta weights in the model. So why we do this is because the statistical model will not approximate the outcome well if the assumed distribution is not a good fit for the space of the outcome. Right? If you don't have a model that really is a decent fit to the outcome, you cannot believe the results that come from the computer. And in big picture cases, this binary distribution is one of the big ones. You can't use a linear regression to predict a binary variable. It just doesn't fit the space of the outcome. So the key to making all this work is the use of these differing statistical distributions. And literally anything is possible. If you can dream up a statistical distribution, you can use it. So generalized models allow for the different distributions to be used. The mean of the distribution is still modeled by the model for the means. And now, depending on the type of outcome you have, the variance of the distribution starts to get a little weird. And that's because some distributions don't have enough parameters, realistically, they don't have variance terms. But really what we're saying here is that the variance is a function of the mean, right? So if you have the variance of y, really it's some type of function of the mean of y. So if you know the mean of y, you also know the variance. So you can't predict both at the same time. That's where this is going. So what type of outcome? These generalized linear models, these residual don't allow for some non-normal distribution. There are a bunch of these distributions that are out there. We may have binary data. That's the focus of today's example. We have unordered categories, right? Or maybe ordered categories. This set right here, we often call these or model these with something called a multinomial distribution, which is a categorical distribution where you have an outcome that has, two or more categories, each of which has a probability that sums occurring and those probabilities sum up to 1. Now there's certain constraints we can put on the categories. Perhaps the probabilities are ordinally related. Perhaps they're not ordinally related, but generally speaking, then we can use a multinomial distribution in that sense. But what happens if you have count data? Count data, in theory, have a lower bound at 0, right? You can have 0 observations. Perhaps maybe you're studying the number of cigarettes someone smoked today. Smoking is going away as a habit, hobby, whatever you want to call it. And so a lot of people in recent years have modeled a smoking cessation or try to develop interventions to get people to stop smoking. So here, the counts you might observe, or you might be asked somebody, how many cigarettes have you had today? Well, clearly, the counts can't be negative, right? So starting at 0, 0 is the lower bound. But then they are discrete values, right? I guess you could technically have someone say, I had a half a cigarette, but I think in most cases we just say 0 or 1 or 2 or 3. And these positive values, though, they can go anywhere from 0 all the way up to infinity, right? It is a discrete distribution with no upper bound. So that's a weird model. We can't necessarily use a multinomial model for it because there's a fixed number of categories here. So we have to use some other type of distribution that works for it. And one distribution that we often use is something called a Poisson distribution. It's sort of a skewed distribution. It has categorical outcomes, and it has a range that goes from 0 up to infinity, which is a nice thing. There are others. The modeling of count data is really crazy because not all distributions work the same, and so we have these weird mismatch. You pick a distribution that looks like it fits the sample space, and it still may not work entirely. So for instance, there may be too many zeros in one place, right? So there's extra assumptions that come along, certainly gets nuance. But if you're working in an area where this happens to be, if you're collecting data like this, you learn about the nuances as you're starting to build your model for your outcome. We may have censored data, right? Perhaps we have people rate how much they agree with a statement, but instead of looking on a Likert scale where they circle a number, perhaps they are on a computer or an iPad or some type of device, and they have a bar that slides between some continuous range between 0 and 100, let's say. The top end and the bottom end could be censored, right? So there's a 0, there's a 100, and you can imagine someone who really agrees with something, or the people who really agree with something would all pile up over here, and the people who really disagree would all pile up over here, and then there'd be some type of distribution in between. This is yet another type of model, right? We may have a normal part to it, but we may have categories as well. This is something we call this a mixture distribution, really. So we all have all sorts of types of ways that outcomes can look when you're working with data. And the key is we have to figure out the best model that matches with it. Here are some sets of distributions. I've grabbed this from my favorite, Wikipedia. And for instance, what this tells you is the name of the distribution. It tells you the support of the distribution. This is another way of calling sample space, or the range, right? Where the data can be, right? So normal contains all the numbers in the number line. There are some distributions that only go from 0 all the way up to positive infinity. There's the counts from 0 up to positive infinity. Today we're working with this thing right here, an integer. It says Bernoulli here, but that's also part of a multinomial distribution as well. And so with this, there's also something that comes along, talked about by the link function and the link name for it, and the function of the mean that goes with it. So in a linear regression, if we had all of our betas put into matrices, which we'll see in a future lecture, that would be the set of predictors that would be the model for the means, and that's exactly what it's doing. It's giving us the mean of the outcome for it directly. But these other distributions that are out there, we have to take some type of function of the mean to allow the mean to be on the same space as where the mean would be in the outcome, right? So this mean of a Bernoulli variable can only be between 0 and 1, and we're going to talk about this a little bit more and unpack what's in this circle here. So for right now, let's just not even go there. But you'll note it's a function of the mean. There's some type of way we essentially transform the mean itself. Now, we're not actually transforming the data. The transformation process in this function works behind the scenes in the maximum likelihood estimator. So there are 3 parts to a generalized model. There's link function, right? This is how this link function takes predictions and maps them onto the space of the outcome. Right? There's the model for the means, right? That's what gives us our predictions. And there may or may not be a model for the variance. But it also provides potentially parts for our predictions as well. So the generalized models work by doing this mapping from the theoretical portion of the model on the right-hand side over to the sample space of the outcome on the left-hand side, and that's where that link function comes in handy. Now, the link functions are often nonlinear functions, right? Meaning that there's no linear, no straight line between the two. It's sort of a bendy or curvilinear type of line. And generally speaking, that we end up using them when we have outcomes or sample spaces or really ranges of the mean that don't fit the whole number line, that don't have all the numbers that are possible. And link functions are also expressed for the mean, are typically only expressed for the mean of the outcome variable, although sometimes you'll see it for the variances. Today we are going to focus on that. Right? We're going to look at the mean outcome of a binary variable as we go forward. Generally speaking, though, in other models, the variance can be modeled. There may be even a link function for the variance. We won't go there today. And this variance, typically in generalized models, though, the variance is some type of function of the mean, meaning if you know the mean, with a given distribution, you know the variance as well. So this is the math behind it. Probably should put this second, but let's just go through this real quick. The link function, so if we have our outcome, y, and we want the mean of y, sometimes we put it in a expectation, right? The expectation of y, or really mu of y, which was in Wikipedia. We take that, and what we want to do is we want to predict it with our linear predictors. But our linear predictors give us a number that goes from negative infinity to positive infinity, and our mean, for instance, today, goes between 0 and 1. So we need something that converts this range right here to that space. So there's a function. This typically gets called the inverse link function if it's being applied to the predictors. But if it's applied to the mean, it's called the link function, right? So sometimes you see this as the opposite, which is g of mu of y equals beta 0 plus beta 1 x plus, like that. So g is really a function of the mean. G to the raised to this negative 1 power is called g inverse. And whereas the function of the mean takes the mean, right, which is on this range, 0 to 1, and maps it onto the space of negative infinity to positive infinity, the inverse link does the reverse mapping. It says, nope, I'm going to go from negative infinity to positive infinity back to 0 to 1. So the funny thing about this is you've been doing this already, although the link function was pretty ridiculous. This allows me to introduce the concept of a model being subsumed, which means what we've done in linear regression is already a part of the generalized linear model itself. What I mean by that is, in linear regression, our link function, g of mu of y, was equal to 1, right? What's that mean? Well, it's 1 times the linear predictor, right? So it's 1 times beta 0 plus beta 1 x, so forth, right? So this is sort of a trick, right? We didn't do anything to it. So if we just multiply the whole thing by 1, it doesn't change. So that's what we call the identity link, right? It's sort of a trick. So we've been doing this already. So what I'm trying to say is, in statistics, there's this process of a discovery where we'll learn one model and we'll learn it really well, like for instance our linear regression model. But then we'll learn a new, more broad version of it, and what we'll see is that our previous learning still fits into our bigger expanded picture of things. And so that's why generalized linear models include the normal outcomes or the conditionally normal outcomes that we saw in the general linear model, because we have this very kind of ridiculous link function. We could also talk about the variance too. The variance, again, not all distributions do this. Today we don't necessarily do that, but we won't actually talk about the variance in our example with the binary variable because there's no spot for it. But in the normal distribution, remember we had two parts. We had a mean and a variance. So over here, this is like our expected value of y hat, right, or mu of y, and that's where the model for the means worked, beta 0 plus beta 1 x plus. Right, so the predicted values were there. But over here, the variance of y, we just typically had a very ridiculous function. It was just also one number. It was a parameter, sigma squared. Sure enough, though, this is, by the way, with this one number, it applies to all possible means that happen to be there. So this is where that assumption of constant variance comes from, or homoscedasticity. If you're in the business like I am, get used to saying that like every year. It just rolls right off the tongue. So this variance, though, there's nothing actually stopping us from providing a model for the variance. In fact, we can actually come up with a model that allow us to predict what the variance happens to be. Right? So we could actually go and provide some type of prediction for the variance. Right? So if we took the variance, what's the range of the variance? It goes from 0 up to infinity. So we need some type of function that maps 0 to infinity onto the positive number line. Right? We might call this maybe the log. The log function takes anything between 0 and 1, I guess 0 not inclusive and 1, and maps that to a negative number. And anything above 1, the log of 1 becomes 0, and the log of anything above 1 becomes a positive number. But now we can model the log itself maybe as a function of x's. Now I'm just going to use gammas as a term here. Right? So we could still now have a model that's heterogeneous, variance, or heteroscedastic if we wanted to, and model that with some of our predictors even. We don't typically do that. We don't get into that because in the classical sense, when we use least squares to estimate our linear regression, there's no place for this. But if we flip over to maximum likelihood, which is a pretty straight, direct flip, we can do this just as easily as we can predict the mean itself because there's a spot for it in the model. But we're going to see today that most of these distributions we work with, the variance itself is some function of mean. In our normal linear model or general linear model where we have conditionally normal outcomes, the variance and the mean are independent. And that is one of the only distributions where that happens to be the case. So there's nothing stopping us for providing even a model for the variance in this sense. But again, I'm getting ahead of myself. Let's get into an example. Enough of this theory stuff. Today's example comes from a website at UCLA. And it's an example data set where we had 400 college juniors looking at factors that influence their decision to apply to a graduate school. So the outcome that's in the data set is a student rating of whether he or she will apply to a graduate school on 3 different numbers. If they gave a 0, they said they were unlikely to apply. A 1 would represent somewhat likely to apply, and a 2 would represent very likely. Now, this is a 3-category variable, and there are models for that, and we should be using them. But for didactic purposes, to sort of start you on the path to understanding how to use different models, we're going to simplify this a little bit. We're going to lump everybody who were somewhat or very likely to apply into one category, right? So we have a 0-1 variable. People who are likely to apply or people who are unlikely to apply versus people who were somewhat or very likely to apply, right? Again, you wouldn't do that in practice. You would just use a different distribution for the 3 categories. But to get us started, this is a good entry point. Also, on this data set, we have a indicator of whether or not one or more of the student's parents has a graduate degree. We have an indicator there. So a 0 means neither of the student's parents had a graduate degree, and a 1 says at least one of them had a graduate degree. We have an indicator called public that is a 0 if a student is in a private university and a 1 if a student is in a public university. And we have a person's grade point average on a 4-point scale, right, where 4.0 represents straight A's across college. Here are the descriptive statistics for the data. You can see everything that we have built up. And in the R example, you can see how all of this came together with our data. This is the part where I changed the variable to the change the apply variable to something I'm calling lapply, which is the likelihood of applying in 2 categories. So you can see all this from our data. So let's just go back for a second and say, what if we didn't know that generalized models exist, right? What if we used our straight conditionally normal general linear model, a thing we learned before, the LM function in R, to predict this outcome? Well, remember what the linear model is trying to do. It's providing a model for the means and a model for the variances, right? So here, the model for the means, remember, in a 0-1 outcome, this is supposed to be a predicted probability that someone is a 1. Right? The error still happens to be there. But remember, Y is binary. So once we make a prediction, error itself can either be 2 numbers. It could either be a 0 minus the predicted probability, or a 1 minus predicted probability, right? So if the person was unlikely to apply to grad school, then error would be the top one, and if they were somewhat or very likely to apply, it'd be the bottom one. The mean of the errors, though, would still have to be 0 by definition. And so what's going to end up happening is we would find that the variance of errors couldn't possibly be constant over levels of x because, like we assume in the general linear model, right, where they're really what we're after here is the mean and variance of binary outcome are dependent. Right? The mean is the probability, right? So mu of y is equal to the probability that y equals some numbers, 0 or 1 or something like that. The variance of y is equal to the mean of y. Sometimes we call this p of y, by the way. So this is p of y times 1 minus p of y, right? So if you know what y happens to be, if you know what the mean of y happens to be, the proportion of people in one of the categories, you automatically know the variance as well, because you can take the proportion and multiply that by 1 minus the proportion. So what ends up happening in this is if we were using linear regression right over here on the left, our linear regression line wouldn't know to stop at 1 or stop at 0, right? We'd start making predictions that were quickly out of bounds. Really what we need is something like this on the right-hand side, where our predictions have some type of way of turning off effectively, or what we would call this is an asymptote on the upper and lower ends, right? They sort of get closer and closer and closer to 1, but they never exceed it on the upper end, or they get closer and closer and closer to 0, but never go below it on the lower end. So, in general, there are three problems when we try to take our continuous, conditionally normal linear model and use it to model a binary variable. We have a restricted range. We're estimating too many parameters, right? The variance and the mean are dependent in the binary model, but we don't know that. Or the linear model, the conditionally normal model, doesn't know that, so we try to do both. And the residuals can't possibly be homoscedastic, constant. So, enter the Bernoulli distribution, often called a binomial distribution. That's the type of distribution we're going to be using for this outcome. So this is sort of a description of what this distribution looks like. The notation we typically say is our outcome is distributed as the B stands for Bernoulli, where we have a predicted probability for each person. So P, the capital P, is the probability, and lowercase p is for a person. So each person, just like we have in our linear model, each person has a predicted outcome. In the conditionally normal linear model, that prediction is really the mean for a given x and given z and so forth. In our Bernoulli distribution, if we're going to make a prediction, we're going to predict the mean as well, but that mean is now a probability, so each person will get a predicted probability of an outcome happening. So here, so I'm calling this a probability of a 1, but you can call this a probability of whatever you'd like. You could model a probability of 1, but the thing about the Bernoulli variable is it's just easy to model probability of 0. And that's where the maddening thing about software happens, is that each package in R, or each function, or better yet, even in SPSS or SAS, each possible routine that the computer builds does it slightly differently, and it's really frustrating. You have to sort of understand the context with which they're working. I'm only going to show you one today, though, so we're going to work in that context right now. So the sample space. What is the sample space of the Bernoulli outcome? What are the outcomes that possibly? It's either a 0 or a 1. So this matches perfectly with what our data happen to be, where y is 0 if a person is unlikely to apply to grad school, and a 1 if they're somewhat or very likely to apply to grad school. Now, what is the density function? What is the distribution function for this? It is the mean probability raised to the outcome times 1 minus the mean probability raised to 1 minus the outcome. So, for instance, if yp equals 0, what happens? All right. Well, yp equals 0, this side of the model shuts off, right? Anything raised to the 0 power becomes 1. So this f of y equals 0 is equal to 1 minus p. So the probability that a 0 happens is 1 minus the probability a 1 happens. What happens alternatively? The opposite. What happens if y is a 1? F of y p equals 1. Well, again, now the opposite side shuts off because we're raising it to a 1 minus a 1, which is a 0. So we're left with saying that this is the probability of an outcome. Right? So p represents the probability y equals 1, And then the distribution function for somebody who has a 0 says, oh, it's 1 minus b. Or in probability, we often call that the converse. So what is the expectation? What is the mean of this distribution? It is p. Right? It is that parameter itself. So we will provide a model for this thing. In fact, we're going to provide some type of link function for this mean to map it to. So we're going to model that type of, that link transform mean. The variance of y is given by p times 1 minus b. I mentioned this in the previous slide. So therefore, once we know p, we know what the variance is. So there's no opportunity for us to model the variance at all here. So we can only model the mean. So there will be no residual variance in this model, which is a little bit weird. But that's the way these things work with distributions like this. So let's talk about what a link function might happen to be. We have a number, our mean, p, our predicted mean, will range between 0 and 1. Actually, I'll just do this. And so what types of transformations could we use, right? Well, we could take that probability and turn it into an odds ratio by taking p over 1 minus p. Right? So the odds you may have seen before. Often you see this in gambling or betting or some type of outcome related to sports. The odds that some team is going to win, right? And the way this works, if you have a probability of an event occurring, then the odds of that occurring would be that probability, right, divided by 1 minus that probability. So if the probability was 0.7, the odds of the event occurring would be 2.33. So it's 2.33 times more likely the event occurred than didn't. Alternatively, the odds of 0 is less than 1, right? It's much less likely for the odds of 0 to happen, for the event not to occur than for the event to occur. But you'll note when we take p, a number that goes from 0 to 1, and put it over 1 minus p, the range of this odds ratio goes from 0 to positive infinity. So that's half the way where we want it to be, but we want this linked function to give us ranges between negative infinity to positive infinity. And the way that we can do that is take the natural log of the odds ratio, right? Natural log, right? Natural log of p over 1 minus p. Now that changes everything. This is sometimes called the logit link, the log odds ratio. So here, if our probability is 0.7, the odds was 2.33. If we take the log of that thing, the natural log of that thing, we get a 0.846. Similarly, the natural log of 0.429 is negative 0.846. So now, not only is our range between negative infinity to positive infinity, it's also symmetric around 0 in that complementary probabilities, right? This is a 0.7. Probability of the event occurred was 0.7. That means the probability of a 0 was 0.3. But those give us numbers that are either on one side of 0 or the other. They're reflective about 0. So the log odds, or the logit, is the link function that we're going to use today. That's where logistic regression gets its name, the logit itself. But I will tell you that there are many options for the link function that you can choose. And this is sort of where people from different fields tend to rely on different things. For instance, probit model is something you might find in econometrics or business, where we have a different version of mapping a probability onto a real number line. In fact, this essentially uses kind of the inverse, like the z to probability lookup table that you used to have in a statistics textbook. So it's an inverse normal distribution that it does. But these link functions provide just a different scale for the metric. It doesn't necessarily change the story that you're going to tell very much. But there are other ones. There's a log-log link, which, as it sounds, there's multiple logs going on in there. There's a complementary version of the log-log link, which is also crazy. But there's a handful of different link functions that are out there. But logistic is where we're going to start, where we're going to focus just to try to keep things a little bit less crazy. It's sort of there's so much out there that you could effectively take a class on each type of distribution if you'd like to. So what happens is the logit is a nonlinear transformation of probability, meaning that equal intervals in logits are not equal in probability. And here's an example from a book. Here's a logit down here, right? So what does that mean? A logit that goes from -1 to 0 is a distance in probability from 0.27 to 0.5. But a logit that goes from -1 to -2, which is the same distance, now the probability goes from 0.27 down to 0.12. You see it's shrinking as it gets closer and closer and closer. So here is a nice graph of logit. So on the bottom, here's a logit value. On the left-hand side, here's a probability, and we can map the probabilities to sort of give you a sense for what the scale of this outcome happens to be. A probability of 0.5, right? If we lead to an odds, remember odds is probability divided by 1 minus probability. So 0.5 over 1 minus 0.5, which equals 0.5 over 0.5, which is equal to 1. The log of 1 is 0. So the logit of a 0.5 probability is 0. So whenever you see a predicted logit value of 0, you know there's a 50-50 chance the event occurred or will occur. It's a prediction that's completely uncertain. So let's move up a little bit. A probability of 0.9, which is up here, leads to a logit value of 2.2. Right? So this is a high likelihood an event occurs is at 2.2. Well, the cool thing about logits, cool if you're in a statistics sense, is that if you know that the probability is 0.9 gives us a 2.2, you also know the probability of 0.1, right? The complementary probability, right? 1 minus 0.9 equals 0.1. The thing that makes 0.9 sum to 1 gives us that same logit multiplied by -1. So the probability of 0.10 gives us a logit. Here's 0.10, gives us a logit down here at -2.2. Because it's symmetric or reflective about the about around 0. So a logit of 0.99 is a 4.6. So again, if you see a predicted value of 4.6, you know that's almost certain this event occurs, 0.99. So what do you think a probability of 0.1 would lead to on a logit? Well, 0.99 plus 0.01 gives us 1, so 0.01 is complementary to 0.99. So that would give us a logit of -4.6 as a value. So it would be down over here, right there. So what happens in the analysis algorithm? Right, what we're going to do is transform logits to probabilities using our link function and our inverse link function. So in the terminology of generalized linear models, the link function is given by this log of the natural, this natural log. Right? Normally we just say log for it. It's just log base e, which is Euler's constant, about 2.7. So our function of the mean is this logit, the log of the probability of an event occurring over 1 minus the probability of that event occurring. And we're going to take our model and predict that logit. That's how it's going to work. Now, forget all this algebra, but we can always, whenever we do the transformation to the logit scale, so that means what I'm trying to say here is that all the betas that we're going to come out of the computer are going to be in logit units, logits of y per unit of x, which is a little bit weird to think about. It's not just directly y, it's now this logit of y. But anything that we have as a logit, if we form a predicted value, right, we get essentially like a y hat, if you want to call it under here, a predicted value, we can transform back into a probability. The algebra for it is there, but really how we do that is down over here at the bottom, this inverse link. So the expected value, our predicted value, is some inverse link of a function of the linear predictor. In the logistic regression, you get used to seeing this almost all the time. EXP is E, which is 2.71 right about. So that's 2.71 raised to the power of what the predicted value happens to be, over 1 plus that same number. So for whatever we do for a logit, we can always transform into a probability. Because probabilities are a lot easier to talk about than logits are. Similarly, we will also see that anything we can do in a logit, we can also transform into an odds, or an odds ratio. And odds ratios are also very, I find odds ratios really hard to talk about and understand, but a lot of different fields use them. So for instance, in medicine, you might see odds ratios in a lot of the statistics, or a lot of the journals that talk about effects. So the odds of a patient improving based on, some type of intervention or drug or treatment is usually given. The other part of that is that when you talk about effect size for categorical variables, particularly for a binary variable, the measure of effect size that's most commonly used is an odds ratio. So again, thinking this through, the model is still the model. That's where all the magic happens. But now once we're going to get a result, we're going to either transform that back into a probability to describe it, or an odds to describe it. But all three of these things can be switched around synonymously and mean the same thing. So, all right. So basically what we're doing is finding there's nonlinearity in prediction. So you'll see the linear model that we have, the right-hand side, is predicting the logit. So it's linear, what we call linear in the logit. But for the probability, remember, which is the mean of the variable, it becomes nonlinear once we convert it backwards, because transforming logits to probabilities gives us this S-shape or bendy curve right here. Sigmoid function I've heard it called before. So I find the probability version of this is easier to show. The logit version of it will be a little bit easier to explain, because if you're used to linear regression, the logit is linear regression. It's just logits are the outcome instead of y. So when we put this all together, if we take an empty model and we say y is equal to, this is under the conditionally normal model. Let's compare and contrast empty models in these two approaches. In the conditionally normal model, y gave us, beta 0 gave us the mean of y. Right? That was our predicted value. And the expectation, or the error, the variance of error came from sigma squared error. So when we fit this empty model, this is my way of trying to connect a model to data, we would find that with an empty model, beta 0 would give us the mean of the sample, and sigma squared error would give us the variance of the sample. In a logit model, or in a logistic regression, a similar thing happens, right? But now, when we fit an empty model, we just see beta here. We don't have error, because error doesn't have a place for it. There's no place for the model. It's just beta. There's nothing else to it. And because we're only working on the model for the means, that's why we don't need error here. This linear model sort of combined the model for the means and the model for the variances. Here in a generalized linear model, we're only working for the model for the means. So we have beta 0. So beta 0 is the logit of the mean, or another way of saying the log odds of the mean of y. And in our case, the mean of y for a Bernoulli distribution, this two-outcome variable, is the probability an event occurred. So if we wanted to show that that happened to be, we could actually convert the logit to probability, taking e to beta 0 over 1 plus e to beta 0, and we'd get back the probability, which sure enough is the mean of y. And wouldn't you know, if you go and compute the variance from that, p times 1 minus p, you also get the variance of y for the sample as well. So a little bit more on that. There is no error term in the logit model. And it turns out that's because the variance for error happens to be fixed. And you don't have to go too much into this. It doesn't really make a difference until you get into a multi-level model with a logit link function. Really, that's where you start to see it. But really, what people will find is that the variance of error was 3.29, or pi squared over 3, which is, what? I'll put one of these. There we go. Yeah. Statistics trivia. So let's do this in R. Let's do a logistic regression example in R. That's all the theory. Let's get back into the practice here. The package that you will be using the most, at least the one I find tolerable, is something called the ordinal package. All right, so if you go over to my R script, you'll see at the very top, I have this code right here that puts in the package ordinal, if you don't already have it, and we load the library itself. And in the ordinal package, there's a function called the CLM. CLM stands for cumulative linear models, which is really what we're going to be fitting, but with two cases, it's pretty. There's not much to be cumulative about. When you get to more than two categories for your outcome, that's where this really makes a difference. So let's take a look at the syntax for this. All right, so let's go. I'm going to go over here. What we have to do to use the CLM package is we have to convert our outcome, in our case, my case, this lapply variable right here, which is a bunch of zeros and ones. We have to convert that to a factor type, an R factor type. Well, now remember, an R factor is R's way of essentially categorizing the variable, letting R know there's multiple levels. So if I say that the original variable is equal to, I put itself in the factor function, and if I now show the factor, you'll see that right here, R gives me all the data again, but it now tells me there are two levels, 0 and 1. And that's helpful to the CLM function because it will go and figure out what the levels of, will go and try to figure out the parsing of the model based on these levels of your data. So now let's look at the model syntax here. Model 01 we're going to run, which is an empty model. Again, just like LM, we put lapply, put our dependent variable. The tilde takes the place of the equal sign. And if we just want the empty model, the 1 represents the intercept. Again, we tell it the data set or data frame that we're using. And I've added this option control on because I want to show you how the algorithm finds the number. You don't have to use this option very often. It's just showing you this is an iterative algorithm that goes through finding the option, the numbers that we have using maximum likelihood. So if I go and I run this analysis, you'll see that there are iterations. This CLM control trace equals 1 shows the iteration history. And sure enough, the very beginning guess of the parameter was, the parameter again is in this case, the logit, actually the probability, it's expressed with the logit, so it gives me a probability of 0, and it tells me the maximum likelihood value that we're going to talk about. It also talks about the what's something called the gradient, which is effectively like a derivative. We want all of our derivatives to be close to 0. And then you can see it then guessed the probability of 0.2, and it got a new changed the maximum likelihood value, and then guessed the probability of 0.2007, changed it a little bit more, and the next guess was beyond the significant digits reported here, and that's where it stopped. So it says optimizer conversion.